So that last example, example 4, there was no way to write one integral with respect to x and get an answer for the region, for the area of the region. Because, like we said, we had a different bottom curve for part of the region than we did for the other part. So that begs the question, what if we weren't thinking about integrating with respect to x? So I've copied the picture here, and notice what happens. Instead of filling in vertical, infinitely thin rectangles, imagine filling in horizontally oriented rectangles. Still, we're going to have infinitely many, infinitely thin rectangles. They're just going to be horizontal. So now the height of this rectangle is a very, very, very small change in the y-coordinate. I would call it dy. And the width of this rectangle is not negligible anymore. There is width. And notice, since the width of that rectangle lies on a horizontal line, to find the distance of that horizontal line segment, I would subtract the two x-coordinates of the two endpoints. And in order for my subtraction to come out with a positive result, I would start with the further right x-coordinate and I would subtract the left x-coordinate. So what I'm going to have here is, there we go, the right hand x minus the left hand x. So right minus left. So this would be a one integral answer if I had functions for the x-coordinates at those 2 points in terms of y. So notice that what I have instead, what I've been given at the start, is y equals square root of x. If I take that equation and solve it for x, what would I have to do to both sides? Well, to cancel out the square root, I'll have to square both sides. It's going to give me y squared is equal to x. My other boundary was y equals x minus 2. I can solve that for x by adding 2 to both sides. I'd get y plus 2 equals x. And I now have a formula for the horizontal distance across that infinitely thin rectangle. It's going to be the rightmost x, which is the x from the linear boundary, minus the leftmost x, which is the x from the square root function. So that's the integral I'm going to write, and you can see at the top of that next page I have for you another way you can think about integrating. You could orient your rectangles horizontally and integrate from bottom to top of right minus left, where right and left are functions of y. So this is my integral. I'm going to integrate from bottom to top of right minus left, where right and left are functions of y. So I've taken the two boundary curves that I was given originally and I've solved them for x. So x equals y plus 2 and x equals y squared. So my integral from 0 to 2 of y plus 2 minus y squared. Notice I'm integrating with respect to y. You have to be 100% certain that if you're going to integrate with respect to y, that your integrand is a function of y, and that these are your y limits. In this case, the lowest y value that gets colored in, and the highest up y value that gets colored in. All right, so now I'm going to find an antiderivative. That's just y squared over 2 plus 2y minus y cubed over 3. I'm going to evaluate from 0 to 2. I'm going to plug in 2 everywhere I had a y. Then I'm going to subtract what I get when I plug in a 0 everywhere I had a y. So this 2 squared over 2 simplifies to 2. 2 times 2 simplifies to 4. 2 cubed over 3 is 8/3. These all turn out to be 0. So 2 plus 4 makes 6. If I was going to translate that into thirds, 6 is 18/3, and I'm going to take away 8/3. Gives me 10/3. which matches the answer when I got the first time I did this problem by splitting it up into separate regions. There's only one answer for the area, so if I integrate with respect to y, or I split up the region into a couple of different sections, or if you use the technique suggestion in example 7, no matter how I find the area of that region, there's only one answer, so that's important that matched the answer we got before. So there's just one more point I'd like to drive home, because we've done this in all the rest of the examples. Notice if I'm integrating with respect to y, I said I want to integrate from bottom to top of right minus left. So just notice it's pretty clear here that the lowest down y in this problem is y equals 0. The highest up y, that point is clearly marked, is going to be y equals 2. So I want to trace along the right boundary and just confirm for myself that I'm only ever walking along one function. Let's make a different color. So in my right boundary, I'm going to trace along here. That's the right boundary of the region I'm finding the area of. Was I always on the same function? Yeah, I was always on the function y equals x minus 2. And I can double check the leftmost boundary. If I'm going to walk along the leftmost boundary, the left coordinate of the rectangles, if I was drawing in a horizontal rectangle to fill in all that area, I was walking along that orange curve, and the whole time that was the curve y equals square root of x. So that's why this problem can be done with one integral when I'm integrating with respect to y, because if I think about the right and left boundaries, the right boundary is made up exclusively of one curve, y equals x minus 2, and the left boundary is made exclusively of one curve, that's y equals square root of x.